Small sample hypothesis test, example 4a. In a sample of n equals 3 light bulbs, the proportion of defects is p hat 1 out of 3. In order to meet industry standards, the proportion of defectives must be less than p0 is 0.1, and the proportion of good light bulbs must be at least 1 minus 0.1, that would be 0.9. We want to test H0, P equals 0.1, the company does not meet the standard, versus H1, P less than 0.1, the company does meet the standard. So this is a left-tailed test. We only say the company meets the standard if we have less than 10% defective. So we have a less than symbol here. So we want to check whether n times P0 is at least 5. So n is 3, P0 would be 0.1, that's 0.3, and that's not bigger than or equal to 5. Okay. N times Q, that'd be 3 times 0.9, 2.7, and that's not greater than or equal to 5. So even if we have just one no, we have two no's, but even if we have just one no, we have to compute the exact binomial probability. Binomial random variables they're called binomial because there's two possible outcomes for each case. Either the light bulb is defective or it's good, and it's a random variable because the number of defects could vary from one sample to another. So we're going to use a tree diagram and we set up the tree diagram as if the null hypothesis were true, and that each light bulb has a 0.1 chance of being defective and a 0.9 chance of being good. Okay, so here's our tree diagram. So we want to multiply as you go across the tree. So the top path, we have 3 bad light bulbs, 0.1 times 0.1 times 0.1, 0.001. That's 3 bads. And then we have 2 bads followed by good, 0.1 times 0.1 times 0.9, it's 0.009. We have bad, good, bad, 0.1 and 0.9 times 0.1, 0.009. Bad followed by 2 goods, 0.1 times 0.1 times 0.9 times 0.9, 0.081. Good followed by 2 bads, 0.9 times 0.1 times 0.1, 0.081. Good, bad, good, 0.9 times 0.1 times 0.9, 0.081. 2 good followed by bad, 0.9 times 0.1 times 0.1, 0.081, and all 3 are good, 0.9, 9.9, 0.729. Okay, so so then the total will give us our p-value, and that's 0.972. So a p-value of 0.972. Okay, so so that's more than alpha, so we would fail to reject H0. We could also hold on here. I need to correct this here. We want the paths where we don't need all these paths. We only need the paths with at least at most one bad one. So we don't want the ones with 2 bads or 3 bads. So let's scratch off some of these paths here. So we only need the paths with at most one bad light bulb. Good. This one is. Okay, we don't need that one there. So we only need the paths with at least with at most one bad light bulb, and these add up to our p-value of 0.972. And if you're using Pearson MyLab, they don't have capability for trees, so instead of a tree, we make a list, and we only make the list of the, in this case, the paths with at most 1 out of 3 bad. We have bad in the first position, bad in the last position. The one that's missing is bad in the second position. So we want to fill in good, bad, good. And this will be 0.9 times 0.1 times 0.9, 0.081, and add these up to give a total of 0.972. And that's our p-value. P-value is more than alpha, so that we fail to reject H0. The sample does not provide enough evidence to say that the company meets the standard. And this is some of the terminology of hypothesis testing. Either we reject H0 or we don't reject H0, and either H0 is true or H1 is true. Some books use HA, some books use H1, but I'll usually try and put H1 here. 1 minus alpha is our desired level of confidence. Alpha is a Greek letter, represents the desired level of significance. P-value is the actual level of doubt. Beta, usually we won't compute beta. That's the probability of a type 2 error. You need to make some additional assumptions in order to compute that. So we usually will not compute that. And usually it's not computed. Occasionally people are interested in computing the probability of a type 2 error, but usually it's not computed, and we won't be computing it. In this case, because we failed to reject H0, what type of error might we have made? So if we don't reject H0, we take a chance of making a type 2 error. If we reject H0, we take a chance of making a type 1 error. But either way, you take a chance of making some type of error. Okay, example 4b, redo example 4a, if the proportion of defectives is 0 out of 3. Instead of 1 out of 3 defectives, now we have 0 out of 3. And we could use the same tree, but now we only need the bottom path here, the one I marked in red, where all 3 light bulbs were good. Probability there at 0.9 times 0.9 divided by 0.9 is 0.729. So that's going to be our p-value. Is 0.729. It's still more than alpha, so it's still not enough evidence to reject H0. Example 4C, we do example 4A if the proportion of defects is 0 out of 10. So again, there's only one path where none are defective, but in this case we have instead of 3 good light bulbs, we have 10, so it can be 0.9 to the 10th power. That comes out to be about 0.35. So there's still, our p-value is still more than alpha, still more than 0.05, so still not enough evidence to reject H0. And then example 4D, if we if the proportion of defective is 0 out of 40, if our sample size is 40 and there's no defective, instead of 0.9 to the 10th power here, we're going to put 0.9 to the 40th power. So let's say 0.9 to the 40th power, we can put that in the calculator. And that's going to be 0.0148 approximately. Approximately 0.0148. This is going to be our p-value. So that would be enough evidence then to reject H0. If we had a sample of 40 with no defectives, that would be enough to reject H0. And that concludes this presentation.